Okay, so my name is Anastasiia. I'm a fourth year student of system analysis at the National Technical University of Ukraine Kyiv Polytechnic Institute. And today I want to present a project I worked on recently that we actually submitted to ICML, which was a doozy, but a lot of fun. So, calibrated value over stochastic environment models. Quite a mouthful. Let's get into what it all actually means. Okay, let's introduce some notation. As this is for an RL course, I'm pretty sure you guys know what I'm talking about, but let's just get on the same page. So the little pretty S is the state space, A is the action space, which we assume is continuous in our case. The P is a transitional kernel, which just means that it gives you a probability density function over the next states given the current state and the action. And there's also the reward function, which basically defines the entire task in the environment and is a function of a state and an action. Great. Next, some more definitions. The pi here is a policy. So it can be either stochastic or deterministic, we don't really care. It either gives you a probability density over action space given the current state, or just gives you the action. Then the policy condition transition kernel is analogous to the previous transition kernel, but we integrate over the actions, so it accounts for the policy, and we'll keep on using the symbol further in the presentation because we don't care for actions that much, and this allows us to do that. And then the value function under a policy is giving us the expected reward, the expected discounted reward given the starting state. And that's it for the definitions. Okay, so now that we've established the terminology and the actual task that we're trying to solve, how do we actually go about finding the policy, learning a policy given this problem? So one way to do it is to learn a value function. And the value function is this special little function that is the unique stationary point of the Bellman operator. The Bellman operator that's shown in this formula right here is basically the expectation under the current policy of the reward plus the discounted expectation of the value of the next state. So it's recursive and it converges at the correct value function. There's also a generalization to multiple steps. So this formula down here is basically the same thing, but instead of advancing only one state into the future, we actually move multiple steps into the future and accumulate all of the discounted reward that we receive from the environment, and then we take the B steps ahead value function, which is kind of wrong here. Ignore the incorrect indexing here. Okay. So by updating the value function with this operator, we converge at the correct value function, and this is how we basically learn it. Model-based RL is another component of this paper that we need to touch on briefly. Basically, this is a paradigm of reinforcement learning where alongside the value function and policy, we also learn a thing called a model. And by a model, we mean specifically the model of the environment's dynamics. So why do we want to do this? Well, there are multiple reasons. For one, a learned model will give us better data efficiency. So this is the first square here, lifted entirely from this survey paper. It's actually quite good. So data efficiency, how do we get this? Well, by using a model, we can first plan exhaustively at inference time, which means that we will basically converge in planning and then act in the environment, which saves on suboptimal steps potentially. Also, we can use the model to update the value learning and the policy learning by using synthetic model data instead of real-world data, which also reduces real data sample complexity. Another thing that's useful with models is exploration. So basically by planning, you can plan to explore in multiple different ways. You can account for model uncertainty, you can seek out novel states using a model, and so on and so forth. This here is supposed to say optimality. I don't know, the paper must have been wrong, but this basically means that with a model, you can often achieve better performance on average in a lot of tasks. Transfer here means that, for example, in scenarios where the environment and the dynamics are the same, but the reward function is different. An example of this would be a lot of DeepMind control suite tasks. For example, there is a humanoid domain, and the humanoid domain has a lot of tasks in it. which are defined by a different reward function. But the dynamics, so the distribution of next states conditional on the current state and the reward is the same. So learning a model for these dynamics and then reusing this model in different tasks can be really beneficial and saves on time on training the new model. So these two I'm kind of skeptical about. Models have been used for improving safety and explainability, but it's not really the focus of this work and isn't entirely relevant. So let's move on to the next slide. And on this slide, we're going to look at how we actually learn a model, which is a very interesting question. So let's settle on the notation here. ST is the current state. XT is a representation of a state. So ST is what our simulator or like the simulated environment gives us that we take as input. And XT is a representation. So this is some output of some MLP that we call an encoder, generally speaking. And the representation is what we compute things over in the policy and the value function. So the little p with a hat here is the dynamics model. So it takes the representation and produces a distribution over next state representations. And the value function as well, it produces a singular scalar value for a given representation of a state that signifies how good or bad the state is. Okay, so one way we can learn a model is by reconstruction. So here, the next state is encoded with the encoder into a representation. The model is used to transition to the next state. Then it's reconstructed using another MLP, Q, which is a decoder. And this reconstruction is then regressed towards the real next state, which is one way of doing this. I think Dreamer does this, at least one of 3 of them. But yeah, so this is one way to do it. Another way is self-prediction. So this is kind of BYOL style scenario is as follows. The next state is encoded into an observation analogous to how it's done here. The model, the same way, transitions to the next representation, so the representation of the next state. But instead of decoding it into a state, we instead take the next state, encode it with the same encoder, and then we push this model representation towards this representation. This is shown to be beneficial in multiple ways. One reason is that this sort of erases the necessity to reconstruct a state perfectly. So this can be really important in pixel-based tasks like Atari, where there is a lot of the state space, like a large portion of the state is actually something that you don't care for, and it's entirely irrelevant to the reward and to value learning, but you would waste compute time to get a perfect reconstruction here, which is like suboptimal. And here it's kind of alleviates this problem. And the next way to learn a model is value over model learning. Basically, instead of regressing a representation of a state towards the representation of the next state or reconstructing them, we push the values closer together. So we predict the next state, we compute the value of the next state given our current value function, and then we push this scalar towards the value predicted at the next state. Yeah, so these are the 3 ways. They all have their issues, their benefits. The value-aware one is really interesting because it basically postulates that the model only learns part of the environment that are important for value learning, and it has been shown to be equivalent to the Bellman operator that we've discussed prior, once it's been trained for long enough. So basically an expectation that's equivalent. So let's focus more on the value over model loss. This image here is basically the same thing from the previous slide, but we go multiple steps into the future. So the M here means that we transitioned in the environment M times. So basically we ran the simulation, we picked an action, we did this M times, and this is our M steps advanced state. Similarly here, the little hat, the model is used M times. So we simulate transitions M times using the model, and get our little x t plus m with a hat. Now, the value we compute on this representation is regressed towards a Bellman operator of this little v with a dash on top, starting from this state here. So we take, basically, if you remember from some slides before, we take rewards, like we sum up the B rewards we received in the environment, and then we computed the value of the st plus m plus b state. Yeah. Great. So we push this value towards this scalar and we're good. Which is basically what's expressed in this formula as well. It's a bit more intimidating, I guess, but says the same thing. This thing is computed using the model, and this thing is found in the environment. We just need to aggregate it properly. So the SG here means the stop gradient, and it basically means that we do not update the weights of this network using the gradient descent. Instead, we update it using the weights of this network every once in a while. So like in the DQN paper, we basically do a weighted average of the weights of this model and update this one this way. This is a target network. Okay, this is the VAML loss. Now, let's talk about where it's used. So not many people might know this, but the mu0 loss used in this paper that was really great and good and fixed every problem in the entire universe basically uses a variant of this loss with m being greater or equal to 1 and b being greater or equal to 1 as well. TDMPC is another algorithm that actually enables planning in continuous action spaces. So mu0 plans using the methods is only applicable to discrete action spaces. And we can't really enumerate a continuous action space, so this is why this paper was so important. Then ITER-VAML is a theoretical paper that explains how like this value where losses are useful and good, and it uses the same parameters, but it sets the b parameter to 0. And then model-free TD is like a standard TD learning that we all know and love, and it just basically means that we don't advance the model at all because we don't have a model, it's model-free. Okay. What is the problem with VAML losses? And now we actually get into the meat of the paper, basically. The problem is, well, are they calibrated? So what is calibration? In the paper, we define calibration as follows. So when the function class includes optimal functions for the original target loss, a calibrated loss does not lead to suboptimal minima, which is expressed in this formula here as well. So if we minimize this loss, given the transitions from our policy conditional kernel, we average over them basically. This surrogate loss, if it's uncalibrated, will lead to functions, like so the argument of this whole scenario, will lead to functions that are not optimal. So f star is the set of functions that are minimizing the target loss, and this thing will not be a subset of that, which means it's uncalibrated. Yeah. So this is bad. This is a bad thing. We don't want this to happen. So does this happen with the ITER-VAML losses? Yes, they aren't calibrated. They are uncalibrated, in fact. So this formula here, let's walk through this. This is the loss we can actually compute. So this is here, this is the M and this is the B. So we advance our states and multi-representations one step. And we don't do multi-step Bellman operator, we just do a single-step Bellman operator like normal people. So this we can compute over our batches from the replay buffer. But this is what we actually want to compute. This is our target loss. And by minimizing this loss, we actually end up with a model that's correct in the sense that it can be used instead of the Bellman operator. What is this? It's a variance term that arises if we actually compute this expectation. So this is like basically the meat of the theory of the paper. And it takes a bunch of time, a bunch of text in the appendix. So I will not be getting too deep into this. But it is not non-trivial math, just a quantity of it that's unfavorable. Anyways, what do we do with this? Is there anything we can do? Yes, in fact, there is. if we compute a bunch of these things, which is basically the mu here is the empirical estimator of the expected return. So this basically means we use our model because it's stochastic to draw multiple samples, and then we average the value over them. So this is the average value of a few samples from the model. And this is the estimator of the variance of this thing. So this is the estimated variance of the value function given the model. And if we correct our computed VAML loss with this variance term, we actually get a calibrated loss, which is also shown in the paper, and I will also not be getting into much. But this basically means that we can correct our loss function in such a way that if we train our model using this function, we'll actually get a correct model, which is great. It's awesome. So let's walk through experiments. These here are the environments that we're gonna run experiments in. So these are from the DeepMind control suite, which are continuous action space locomotion tasks. So basically, you get these funky little guys and you want to make them walk in a sensible manner. We don't do visual tasks, so we don't actually get the frames, and our model does not learn the behavior from frames of these little guys. Instead, we get vectors of all the joint articulations of the skeletons, and then we learn a behavior on those. Yeah. So these are the results. We present them in the way that was introduced by these guys here, the deep reinforcement learning at the edge of the statistical precipice paper. Basically, on the x-axis, we have a performance and some error bars, because error bars are cool. And here we look at different experiments. So these three use a mu0 loss, because the b parameter is 1. So we use a multi-step Bellman operator with a step of 1. The CVAML is the corrected variant, and VAML is the uncorrected variant. And then VAML det just means that we use a deterministic model of the dynamics instead of a stochastic one. And similarly here, the model split and the corrected and uncorrected thing is the same, but these are the ITER-VAML losses from the ITER-VAML paper, meaning that the B is 0. Yeah. So we can see here that the gaps between the corrected and uncorrected variants are pretty much consistent across different measures. So mean just means that we average over all the experiments, which I think it was about 20 to 30 seeds per configuration here, and we average over like 7 environments. So that's a lot of seeds and experiments. A lot of things are aggregated here. The gaps are more prominent on mu0. On the mu0 losses than on the ITER-VAML, which was also expected because the mu0 loss is kind of entirely wrong. We can see that on humanoid, the deterministic model is actually the best variant for both mu0 and ITER-VAML losses, which is funky but fine. We can see that we almost restore the performance using a corrected model. So yeah, these are the results that we present in the paper. Right now we're waiting for the rebuttals. Yeah, thank you for your attention.